Welcome, everyone. For today's prep, we're going back to limits. So we're going back to our limit notes here, and there was one section we didn't get to before, and this is called L'Hopital's rule. And the reason why we didn't get to it is because, well, we need all of our derivative rules to kind of help us out with this one. So the rule we're going to look at, we can use it when we're investigating indeterminate quotients. So if we remember back, this was a very common problem, calculating the limit as x approaches a, and we had some fraction that we were calculating the limit of. So some function on the top, some function on the bottom, f of x over g of x. And we've seen a few different varieties of indeterminate quotients. So the first one we encountered was the 0 over 0 form. So this is when the top function approaches 0 and when the bottom function approaches 0. The other one we saw was an infinity over infinity form. So this is when the top function approaches either plus or minus infinity and the bottom function approaches either plus or minus infinity. So these were the two types of forms that we've looked at before. And we looked at algebraic techniques to kind of help us with these. So for the 0 over 0 form, a lot of times we would do factoring and canceling. We would also do the conjugate method, things like that. Common denominator, those are some common examples. And then for infinity over infinity, that was our x to the n method, where we divide each term in our fraction by the highest power of x in the denominator. Okay. Worth mentioning, as we're recalling here, for 0 over 0, it's worth remembering that c over 0 is not indeterminate. So just because we have 0 in the denominator doesn't necessarily mean we have an indeterminate form. If it's a non-zero number on the top, well, this was our infinite limits. So if we had c over 0, this is either plus or minus infinity. So we won't be able to use this special rule for this case. And then if we have 0 over c, so if the top function goes to 0 and the bottom function approaches some non-zero number, well, this is also not indeterminate. This 0 divided by a constant is just 0. So just because our fraction has a 0 in it doesn't necessarily mean, it's undefined. All right, so these were the two major indeterminate forms that we've looked at. And all of these indeterminate forms are written as limits where x is approaching a, but similar definitions exist for right-hand limits, left-hand limits, and then x going to infinity and x going to minus infinity. So, just use your imagination there in terms of the extra definitions. All right, so let's get to the meat of it here. So L'Hopital's rule. So what this theorem says is that if we have a 0 over 0 form or an infinity over infinity form, then the limit of that quotient, f of x over g of x, is equal to the limit of the derivative of the top function divided by the derivative of the bottom function, provided this new limit exists or is infinite. So what we're going to do here is we're going to take essentially a more complicated form, a 0 over 0 form or infinity over infinity form, and derivatives normally kind of simplify things down for us. So this is going to hopefully simplify our limit calculation. Now, when we use this rule, there's a few things that we need to show. So first, we have to verify that we do actually have an indeterminate form. So we have to state that we have either the 0 over 0 or infinity over infinity form. That's something you have to check, because there's cases where if you don't have that form, well, then applying the rule is going to be incorrect. It's going to give you the incorrect answer. So this first thing is important. So you first have to verify that you have the correct indeterminate form. Can only use the rule if it's 0 over 0 or infinity over infinity. If it's something else, then the rule is going to be incorrect. And then once you verify that, then you can apply the rule. And when you apply the rule, I want to see in your work the specific step where you apply the rule. So we can put a little h above the step in our calculation here where we apply L'Hopital's rule. Okay, so again, the version of our rule here is written with x approaching a, but similar rule exists for right and left side limits as well as limits at infinity. So, we can do this for all the types of limits we normally calculate. And it's worth mentioning here because now that we've learned derivatives, it's easy to kind of mix L'Hopital's rule up with the quotient rule. So what's the difference between these two things? Well, quotient rule is used to help us calculate the derivative of a quotient. So we're trying to differentiate f of x over g of x. L'Hopital's rule is used to help us calculate the limit of a fraction, f of x over g of x. So we use these rules very differently. So just keep that in mind. If our goal is to just differentiate a function and it's a fraction, we have to use quotient rule. If we're trying to do a limit, that's when maybe L'Hopital's rule comes in. All right, so let's try some examples. See how this works. So let's start with example 1. So we have this fraction natural log x over x minus 1, and we're doing the limit here as x approaches 1. So again, whenever x is approaching a number, first thing we should try is just direct evaluation. So let's try it. So we try our direct evaluation first. Always try it. When x is approaching a number, plug the number in, see what happens. If you get something that makes sense, well then, that's your answer. So if we try direct evaluation, we get natural log 1 over 1 minus 1. Natural log of 1 is 0, and 1 minus 1 is 0. So that's no good. 0 over 0 is never the answer. That tells us that we have to stop there. But it tells us we can use L'Hopital's rule. Excuse me. So we're going to start it again, but now we're going to apply the rule. So let's see how this looks. So all is not lost here. The fact that we're getting 0 over 0, we need to actually show that, because otherwise it would be incorrect to use the special rule. All right, so let's apply the rule. So we're going to put a little h above the equal sign where we first apply the rule here. And so how this rule works is we're still going to be doing a limit, but now we apply the derivative to the top of the function, and we apply the derivative to the bottom of the function. Again, this is not quotient rule. This is a separate thing that we're doing here. All right, so now we differentiate. So derivative of natural log is just 1 over x, and then derivative of x minus 1 is just 1. And this simplifies to the limit of just 1 over x. And then as soon as we have this all calculated and maybe we simplify a little bit, well, try direct evaluation again. And if we do our direct evaluation here, we get 1 over 1, which is just 1. Nice. So again, try direct evaluation again as soon as you apply the rule. All right, so let's try another one. Let's look at example 2. All right, so x is approaching pi from the left. So again, if we're going to use the rule here, then it still applies for left-hand limits. The function in question is sine of x over 1 minus cosine x. So first thing we try is just our direct evaluation. Again, whenever x is approaching a number, plug in the number, see what you get, and if you get something that makes sense, well, then you're done. So if we plug in, what do we get? Well, we get sine of pi divided by 1 minus cosine of pi. Now it's kind of hard to tell. Is that indeterminate or what it is? So we do need to know what sine of pi is and what cosine of pi is. So sine of pi is 0. And then cosine of pi is negative 1. So we end up with 1 minus negative 1. And if we simplify that, we get 0 over 2. And it's a natural response. As soon as you see a fraction with 0 in it, you throw your hands up and you get scared. But it's not too bad. 0 over 2 is just 0. So as long as we don't have division by... Ooh, choking up here. As long as we don't have division by 0, we're good. So 0 divided by 2 is just 0. So we don't even have to use the rule. There's our answer. So note for this one, using L'Hopital's rule would be incorrect. You'd get the wrong answer because it's not of the correct form. It's not 0 over 0. It's not infinity over infinity. All right, so let's. You want to do one more? Yeah, why not? Let's do one more. All right, so let's look at example 3. We've got e to the x over x squared. Now here, x is approaching infinity, so we can't really do direct evaluation, but we can think about what happens to the numerator as x gets really big and what happens to the denominator. So if we think about what's going on, x is going to infinity. So if needed, we can still use L'Hopital's rule for limits where x goes to infinity or x goes to minus infinity. But let's think about what's happening to the numerator. So as x gets really big, e to the x, try that again, e to the x also gets really big. So the numerator here goes to infinity. And then as x gets really big, x squared gets really big. So that goes to infinity. So we have this infinity over infinity form. So that's not the answer, but that tells us we can apply our special rule here. So we're going to try it again. So we're doing the limit of e to the x over x squared, x going to infinity. We're going to apply our rule. So again, I want to see the specific step in your work where you apply the rule. So put a little h above the equal sign there. And the way the rule works is, well, we rewrite our fraction and we apply the derivative to just the numerator and we apply the derivative to just the denominator. Okay. Again, not quotient rule. So then if we differentiate, derivative of e to the x, nice. It's just e to the x. Derivative of x squared is 2x. And we're still doing the limit here as x goes to infinity. Once you actually calculate the derivative, see if there's anything to simplify. In this case, there's not too much to simplify here. So then normally you try your direct evaluation again. But in this case, we're dealing with x approaching infinity. So you just want to think about what's the numerator doing, what's the denominator doing. So in this case, e to the x still getting really big. And as x gets really big, 2 times x is also going to get really big. So that's also going to go to infinity. So, well, we've done L'Hopital's rule once, and we still have an indeterminate form. So sometimes you have to use it more than once. So we try it again. So we have e to the x over 2x, limit as x goes to infinity, and we're applying the rule again. But the thing with derivatives is for powers of x, they usually simplify our powers of x. So a lot of times if you do the derivative enough, it'll kind of simplify the powers down. So in this case, we're going to apply the derivative to both the top and the bottom again, the way L'Hopital's rule works. And if we differentiate e to the x, well, still stays just e to the x. And if we differentiate 2x, we get 2. All right, so now we think about, well, what's going on with this function? So e to the x still going to infinity, but now the denominator here is just staying constant too. So we have this term that's getting really big, and it's going to make the whole fraction get really big because the denominator is just staying 2. So this whole limit goes to positive infinity. All right. So L'Hopital's rule is going to be helpful here. And just a reminder, when you do these, just want to see a few things in your work. So you first have to kind of state what form it is. So infinity over infinity. And then show the specific step in your work. So you can just indicate that with a little h on top. All right, so we'll practice more of these in class, and then we'll also see how we can kind of use L'Hopital's rule to help us with maybe some other indeterminate forms, so some indeterminate products. So we'll see you then. Bye-bye.